Thank you very much, Clara. It's again wonderful to see GIB out supporting another important industry event and making these sorts of opportunities available to the industry. So thanks for that. And I have to say it's a pleasure to be back in New Zealand. It's a country that has a great deal in common with Canada, not just its colonial heritage and a lot of its culture and legal system, that type of thing. But as everyone here in the room probably realizes, our climates are almost identical. And so I've been in the tropical part of New Zealand. I'm still feeling this is semi-tropical, and this is your summer, isn't it? And, yeah, so you'll find that the buildings are designed a little bit differently in Canada, but really the dynamics aren't much better. We simply add a bit more insulation to prevent us from freezing to death. And, but other than that, they're really very similar. And so this trip, though, has been not only enjoyable to be back, but also educational. I knew before coming here that quantity surveyors were an important part and an essential part of the market transformation process. But in working with the New Zealand Institute and the meetings and talking to a number of people, it's really become apparent what a powerful component of that transition quantity surveyors can be. So that's really the message I'd like to conclude on today. But throughout the presentation, we'll keep the enjoyment going because I was part of the group that went mountain biking yesterday. And I'm busy trying to pick out people in the crowd to see if I can recognize them without mud all over. So we'll see. It's interesting to see who cleans up. You know, they're not even recognizable. So they did let us back into the hotel, however. That was very generous. So, all right, so today what we'll do is just have a bit of a quick run through of several topics. First of all, just a few words on the broader international global policy context, and then offer some descriptions of the various sort of building labels that are out there that are put forward as solutions. Some words on project costing and how that works in terms of high performance buildings, and then wrap up with some slides on the role of quantity surveyors. Now, all of you who are doing any amount of reading will have heard a great deal about various policy initiatives around the world. It's a global thing. It is happening at different rates in different countries, and of course things sort of wax and wane with elections. But the overall trend is undeniable, and it's actually unstoppable. The climate change imperative is going to become increasingly urgent as the impacts are felt more acutely. And the types of policy initiatives you see listed there are simply going to become more common. And I've included the one there from New Zealand, the Zero Carbon Bill, along with a long list of others. This list is nowhere near complete. You'll see these sorts of things all over the place, and I know that New Zealand will have other policies, and there's certainly work being done to develop future policies. So this sort of stuff is going to increase. And the question is why? From the public policy perspective, why are governments around the world paying attention to buildings, I would suggest more than they ever have before? And the reason is illustrated on this graph, and as Clara alluded to in the introduction, buildings consume up to 40% of global energy use, and they contribute up to 30% of annual greenhouse gas emissions. There is no country that has signed the Paris Agreement that can meet its commitments under that agreement without addressing buildings. And they need to address buildings not just by tinkering around the edges through incremental improvement. They need to transform how buildings perform. And that is what's driving all of these public policy initiatives. And as I was saying, that's not likely to slow down because as long as these factors these numbers remain much like they are, the climate conditions are going to become more severe. So there's a variety of labels that are put forward. There's lots of green building labels. You hear about it all the time. Net zero. Does anyone here like to take a stab at throwing out a definition for net zero? No hands early in the morning in front of all these people? Not even the ones with mud on your faces yesterday? Okay. Well, net zero commonly is just taken to mean a building that over the course of a year generates as much energy as it consumes. In most definitions, it is assumed that energy storage is free, that you can generate excess energy in the summer and then store it for free until winter and then use it then and it counts. So it's just sort of an annual tally of generation and use. Net zero ready is a label that the Canadian government was good enough to come up with, because of course net zero isn't really carefully defined, and you'll see sort of different wrinkles on it. Net zero ready really isn't defined anywhere, so it is something that all the politicians can agree on. So that's what we've done. The EU did the same thing, by the way, nearly zero. They're going to require nearly zero energy buildings by next year. And then 18 countries squabble over what nearly zero means for the next 10 years. They all come up with their own definitions and so on. So but net zero ready is just intended to mean a building that is ready to be net zero. So presumably built to a standard where the renewable energy can be installed at a later time. And then nearly zero is a very low energy building that doesn't need much to sustain itself. And it doesn't necessarily talk about the renewable component. Now, zero carbon is another standard that's coming out. It typically refers to a building that in its operation doesn't generate greenhouse gas emissions. It can also, and in many cases does, refer to a building that minimizes the carbon impacts in construction through the choice of materials and construction methodology, or purchases offsets to compensate for the carbon emissions that arise from construction. Passive house is a label we're going to come to more, so I won't get into it here, but it's one of the sort of labels or standards that you'll hear about in the broader context. So the question that comes up quite often is it enough to be low carbon or net zero? Is this just an energy discussion? I mean, clearly that's the driver of public policy, is to get the emissions down. But is that enough? Are we going to be able to transform the market if we don't look after other factors? You know, bear in mind a tent can be net zero if you've got a football field nearby for solar panels. So are we going to transform the market if we have poor quality buildings that are net zero or low carbon in their operations? Are people going to be in a drafty, cold, unhealthy building? I would suggest the answer is no, and some guidance on the topic of what other people are thinking can be found in the 17 UN Sustainable Development Goals. And if you read those 17 goals that the UN is really focused on in many of its policies and initiatives, you'll see that about half of them are relevant to buildings, or buildings are relevant to about half of them. They include much more than environmental sustainability, than energy emissions, or energy use. They include things like affordability, comfort, health. So it's much more broad-based from the UN perspective. So when we were working on the framework guidelines for energy efficiency in buildings with the UN Economic Commission for Europe, we developed this graph. And what we've got is a horizontal axis that represents the quality of life in buildings, with a poor quality of life on the left-hand side and excellent on the right. And the vertical axis is carbon emissions, with high carbon emissions at the bottom and zero carbon at the top. So traditionally, over the course of history, we've, in very broad terms, each dot sort of represents buildings on the community scale, so an aggregation of buildings. We've gone generally from relatively low carbon, low quality of life buildings. Think of the very old, simple buildings made out of largely low carbon materials. They didn't burn a lot of carbon. They were terribly uncomfortable and drafty and cold, but they had relatively low impact. And then we improved the buildings. And for the most part, what we did is we improved buildings by increasing their carbon impact. We made greater use of materials that had more impact, and we started adding fuel and energy to the buildings to keep them sustainable, and we got that fuel and energy from carbon-related sources. So over time, the buildings became better in that they offered a better quality of life, and they became more carbon intensive. That trajectory, though, will curve back as the red line shows, and it does that for two reasons. Number one, we have come to the point with many, particularly larger buildings, where we have a relatively weak envelope and a complex mechanical system to maintain indoor quality of life, comfort, air quality, that type of thing. Those systems require proper commissioning and maintenance, which they don't always get. And we've often designed buildings in a way that they simply don't perform as predicted. We have promises when they're in the design stage, when you're applying for your planning permissions, and the actual operating results are vastly different than that. That's a common fact around the world. So what happens with those buildings commonly is their performance deteriorates over time as the equipment and other components start getting old, not being maintained, that type of thing. They go down. And the other thing is that these buildings are susceptible to climate change. So as environmental conditions change, they offer a poorer quality of life. They don't have the resilience, they don't have the ability to adapt to hotter conditions, for example, to stronger storms. And that's why we see this curve over time is going to come backwards on us. The imperative when we were doing that work was to shift the trajectory of buildings up into the upper right-hand quadrant so that we've got low carbon, high quality of life buildings. And what we can do then is we not only have the power of the policy direction of government driving market transformation, but we're offering better buildings to the public, to business owners, and we can combine the effective market demand with a policy imperative. And the thinking being that when you combine those two forces, you have enough capacity to overcome market inertia. So in Passive House, we're all about building physics. Inertia is a force of physics, and we're looking for ways to overcome those forces and deal with them. So that's the thinking, is we should be looking at both factors. And we're not asking people in delivering modern, better buildings and sustainable buildings, we're not asking people to sort of put on that hair shirt and save the world. We're offering them a better product that incidentally will also save the world. So that to us is an important distinction. Now just some examples of these buildings and the type we've seen. One is the Bank of America Tower in Manhattan in New York City. It's a LEED Platinum building, and it uses, I'm told, more energy per square meter than any other building of its size in New York City. And it's better than it could have been. It's designed using a reference building approach, so there would be data showing that it could have been much worse and still complied with their building code, but it is not high performance. The other two buildings are both Passive House buildings. The first was the center one, the Bank Tower in Munich, was the first high-rise Passive House building, and symbolically it was built by the bank on the former site of the OPEC World Headquarters, which just seemed to be a good place to put a building like that. The other one is a student residence at Cornell Tech in New York City. It's been occupied now for a year or so. So those buildings should perform as modeled. And if you look at the performance data, I haven't seen it, but typically that's what these high performance buildings will do, is they will operate much as designed. And they're the ones I would suggest that we're looking to emulate. So as we move forward, what other types of buildings might we see? This is a rendering of a project that's just received planning approval in my hometown, well, a small community right beside the city of Victoria. It is a modular, mass timber, 12-story, affordable condominium unit, a condominium building. So it's 83 units targeting middle-income families and individuals. and it'll start construction later this year. But it's incorporating new construction methodologies with being modular and in 12-story mass timber. It is going to be, first of all, have a very low embodied carbon count. And when we take a look at the back side of that building, we can see some of the ways in which it's different. The circulation has been set up to be exterior. That's not common in Canada, but a climate where we happen to live, it's really quite doable. And that will, in a variety of ways, keep the cost down. You think of the size of the thermal envelope, it just dropped a whole bunch. And a whole bunch of services to ventilate and to heat and cool the corridors just disappeared. So and what the architect has done has designed those circulation areas to be social spaces as well. So there's large enough places there where people can congregate, the kids can play, that type of thing. And you create community in a building by improving the design in this way. So he's taken this, Oliver Lang is the architect that's been leading this initiative, and what he's done is he's looked for ways to make high performance easy and therefore affordable. He's changed how he designs buildings so that that becomes possible. He's looked for a manufacturing process that can mass produce this type of thing, and they're going to be delivering it starting this year. His group, this team, the project team that they put together, was just awarded a contract in the city of Vancouver to deliver 578 units of housing over 5 buildings up to 16 stories tall using this construction system. So this sort of thing is starting to roll out in some volume. Now the fascinating thing is that when you do a life cycle analysis on this building for its carbon footprint, it starts its life as a significant carbon sink. And then it uses, because it's a passive house, and because it's on a low carbon grid, we've got hydroelectricity in our area. So you connect this passive house to a low carbon grid, and the amount of carbon it uses each year is tiny. Do the life cycle analysis out over 100 years. It takes about 100 years for this building to move out of the carbon negative category. So it's carbon negative for about 100 years, depending on the assumptions you're using. And this sort of thing is possible and it's affordable. And once people experience it, it's likely the direction things are going. And not necessarily saying wood, there's lots of materials to build out of, but this sort of high performance, low impact buildings are possible today. So coming back to the question I skipped over earlier, what is a passive house? A passive house building is one that's built according to criteria that are all based on building physics, building science, that were identified as a result of an EU-funded academic research project. The Europeans had an energy crisis back in the 1980s. They hired a bunch of academics to go around the world, look at these very low energy buildings, try to identify an economic sweet spot for them and figure out what it was that was making them work or not work, as the case may be. So the academics did just that. They gathered the data, and they found that once you get efficient enough, once the building is high enough performance, you can actually cut a bunch of costs. Systems become simpler. You are at a certain level of performance required to design differently, and that can be more economic. So what they concluded was that that level was an appropriate place to say, this is good enough. This is the target we should be aiming for. And the level actually is tied to condition and building physics, and it's the heat carrying capacity of air, so that it is possible in a building like this to deliver the heating and cooling via the ventilation system. That isn't always a good choice, because heating cooling loads are often different than the ventilation loads in a given space, but it is an option, and it certainly improves flexibility and choice in the design and limits the size of the systems that are necessary. So that's a big part of the cost equation. But that's how it came up. There are specific performance targets. They are all just based on these sort of building physics principles. The performance requirements are windows are there so that the inside surface temperature is warm enough. You do not get condensation. You can't get the mold and mildew, that type of thing. The thermal bridge-free construction is the same purpose. You can't let the cold or the heat in through the building envelope, so you keep it thermal bridge-free. And it's the same sort of thing. All the inside surface temperatures need to be warm enough. You can't get the condensation on those surfaces. It also includes various criteria for comfort and air quality. Mechanical ventilation is required. And the hygiene requirements typically refer to that sort of mold and mildew-free environment and having filtered air through the ventilation system. So with all of that, they throw on some quality assurance. And if it's done properly, and you use that energy model that's listed there and complete the energy model properly, the performance gap should vaporize. So there's been thousands of units that have been monitored and verified over many, many years, for up to almost 30 years now. And each unit can vary a little. There's user variation within a building. But you look across the field of them, you get a reasonable sample size, and these buildings will perform as modeled. So the performance gap issue is just a matter of dealing with an accurate energy model and using appropriate inputs for it, and the performance gap doesn't need to be there. So in looking at what it takes to do that, what are some of the actual building characteristics to deliver a building that performs in that way? Well, number one, and we'll come back to this as well, is a compact form. You want to reduce your area to volume ratio. The envelope area needs to be as low as possible relative to the enclosed building volume, because it is through that envelope that you absorb heat on hot days or you lose heat on cold days. So you want to start with something that is as efficient a form as possible. That's very important with little buildings. It becomes much less important with large buildings. But it's still always a factor that you want to look at. Throw in a highly insulated envelope that is airtight. It will require high-performance windows that are properly installed. We'll come back to that in a minute. A thermal bridge-free design. I know in our market, we just love those concrete slabs that carry right on through the envelope and go out into the balcony. And in Canada, we call them heating fins. In other climates, they might be heating fins. But you look at one of these high-rises with those balconies coming out all the way, and what we do in our courses is we put an image of one of those high-rises beside an image of an air-cooled motorcycle engine and ask you to tell which is which. Because it's the same principle. There's widely used external shading, and I see quite a lot of that around New Zealand already, so that won't be so new in New Zealand, but it's certainly relatively new in other markets. And then there's a high-performance ventilation system thrown in. The services within the buildings need to be efficiently laid out and designed with high-efficiency components, because it's not just the heating cooling energy that's counted, it's the entire energy use of the building that is counted. It's a separate number, but it is counted as well. And so then you get this overall package. And for large buildings, the heating and cooling is typically something that can be done, could be designed within limits relatively easily, unless there's really high internal heat gains. But the equipment loads, the plug loads and all this sort of thing is very tricky, partly because we've never really paid attention to it. A lot of our equipment isn't even labeled for energy use. They're doing a hospital in Frankfurt, and nobody had any idea how much energy an MRI used. This building here is going up in Surrey near Vancouver. It's a community recreation center and a library, and it is, in designing it, there's a bunch of gyms, fitness rooms in it. What they saw was the exercise equipment was going to drive the energy loads through the roof. You'd think exercise equipment could be a source of energy, but it actually turns out to be an energy hog as we design it. So they had to source different exercise equipment that was more efficient. If we do all that, what do we get? This is a graph for Canada, and I'm sorry I don't have one for New Zealand. And it's residential buildings. We use a similar type of graph for commercial buildings. The numbers are a little different, but the story is the same. And what we see is the blue bars represent the typical energy consumption of a Canadian residential building taken from national database sources. The red, or the red crosshatched bars, represent passive house. So the 15 for space heating for a passive house there, that's the worst passive house. It's not the average passive house. The blue bar is the average residential building, not the worst residential building. So they're not directly comparable, but still the difference is apparent and it's dramatic. And in other climates, that bar, it may be, the cooling might be the big area for saving rather than the heating. But the heating and cooling typically uses most of the energy in a building, and that's the area where we can therefore make the real savings. That's what needs to be attacked first. The other items need to be optimized, and there's less that can be gained there, but still, with a high-performance building, you've got to look at all of them. And then the last one is space cooling. That's really, in Canada, for most residential buildings, a bit of an afterthought. There's more and more getting cooling now, but the building stock traditionally didn't have it or didn't have much of it. And we can see the energy loads go up for a passive house in terms of cooling in Canada. Any thoughts on why passive house might have higher energy loads for cooling? I hear some vague thoughts. Anyone care to speak up? Yes?
Because it's so airtight, trying to get airflow through the building.
Yeah, the air tightness is a factor, that's right. Any other thoughts? I saw another hand just a little further back.
Less drafted, less thicker glaze.
Yeah, the glaze. Pardon me?
The number of air changes per hour.
Yeah, it's airtight, so you won't get the drafts going through it and cooling it that way. All right, no, those are all factors. The biggest factor, however, is that part of being a high-performance building is it's got to be comfortable year-round. Most of our existing buildings aren't. So in some of our climates, like Toronto, it can be hot and muggy and it doesn't really cool off overnight. You actually need some cooling. And currently, these buildings, they get up to 30 degrees, and then you know it's summer. But in a high-performance building, that isn't an acceptable temperature. So we require that cooling get put in where it otherwise may not be. And then, of course, there's the other sort of factors that come in, but really it's the requirement for year-round comfort that tends to drive the loads up more than those other factors, I would suggest. Now, a few other characteristics. If we've got a true high-performance building, we can use that as a foundation for other standards. We can, if the building itself is high performance, the renewables become much more affordable. They become viable. They become viable on a grid scale if we've got the energy loads for the building down enough. The whole picture then makes sense. So that it becomes an affordable path to net zero. If you wish to make choices on materials, that's a really simple thing to do. The hard part is getting the overall energy loads down. The easy part is swapping out materials. So that's pretty easy to do. And if we're looking for multiple benefits, as I mentioned with the UN initiatives and so on, these buildings will provide that inherently. If you look after those energy flows, the multiple benefits of health and comfort come largely because the building is insulated or isolated from the external environment. You've got this envelope that can protect the inside. The other point that's really critical, and particularly in cities like New York. New York got hit by Hurricane Sandy, and ever since then, they've really been pushing the game, and they're a real center of passive house buildings and scaling up the buildings that they do there. But a big driver for them was resiliency. When the Hurricane Sandy hit, people were without power for a long period of time. They want buildings that can remain habitable when the power is out. Everybody wants buildings that can remain habitable as the climate changes. We're building buildings today that should have a 100-year life cycle. Are they going to be habitable in 50 years? And when we do the modeling, the climate modeling and the building modeling, we put the climate 50 years out into today's building energy models, we see that overheating, in our climate at any rate, is a huge problem, and we know that much of our existing building stock is not going to be habitable at that time. There's going to be a great business in retrofits. We're going to be putting exterior shading on all kinds of buildings that were not designed for exterior shading. So that's just a little business opportunity for anybody. But, but that resiliency is a real factor. And in developing nations too. I mean, that's really what you want, is a simple building that is inherently comfortable and healthy to live in. So the characteristics that I've referred to with high-performance buildings, everybody who has ever lived or worked in one will start with the top 3 factors, and it's comfort, comfort, comfort. They don't talk about anything else, and typically, that you can sit beside the windows in the winter and there's no chill off the windows because the inside surface temperature is warm enough you don't get the radiant cooling. There's no draft off the windows in the winter because again, the inside surface temperature is close enough to room temperature, you don't get those induced drafts. So your feet stay warm. There's no cold air coming out across the floor. It's a very different feeling. It's a stable temperature. It's 20 degrees everywhere. And 20 degrees actually feels warm. We don't need 21 because it's 20 everywhere. It's not 15 on the floor and 22 at the head. So that consistency of temperature makes a huge difference to the comfort and the perceived comfort as well, which is really what comfort is. But that far and away is the #1 criteria. Then people most commonly identify air quality. That is just a function of high quality mechanical ventilation. But you can feel the difference when you move in. And we put an air sensor in a monitoring device that's simple and easy to buy at sort of a consumer level in our home. It monitored temperature, humidity, CO2, indoors and outdoors, and also noise levels. And we put it up in our home for a while, and it's pretty much flat, right? And you can see when people come and go within the CO2 levels a little bit, but not much. And then we sent it over to a neighbor's place. It was a very average home in Victoria. And when you plot that graph, because this outfit will generate a graph of all those factors, and all of a sudden the CO2 levels are going like this. The first thing that happened when we took it over to the neighbor's place is the CO2 alarm went off because they had some friends over. And it's just huge spikes up and down there. And the noise level, with the decibel level, you can hear their furnace. You can just see it on the graph every time the furnace kicks in. And the temperature variation is much higher too, even when you leave the sensor in the same place. You know, if they leave it on the kitchen countertop, it'll be reading the temperature there. But if the real kicker with a conventional building is that if they were to put it down on the floor or in the corners or up in the ceiling, like in different parts of the house, different places, they'd get vastly different temperatures. So that consistency is really important. These buildings are also quiet. You close the windows and doors, the exterior noise goes away because of the quality of the envelope. And of course, the health factors we've mentioned because of the mold and mildew. So those are the key characteristics that are being delivered by this type of construction. Some buildings, of course, have special uses. That may be a server farm. I've mentioned a hospital. We do swimming pools, supermarkets. They all have special uses. A simple multi-unit residential building, by the way, that's our term. We call that a MERB. We're not able to say multi-unit residential building. So this is a 6-story wood frame building. It was the first larger passive house to be built to be completed in Vancouver. And, but it's got retail on the ground floor. And there may be some hugely intensive restaurant use in there. And there needs to be other allowances. So for high performance buildings, we don't actually know how good a hospital can be in Auckland or Dunedin or other cities or in Vancouver. And this is an area where we need to explore. The approach that Passive House takes is, well, we know what another 1 or 2 hospitals have done. Let's see what you can do. And they require that the envelope be as good as it can be, so at a Passive House level, and that all services appear to be optimized as best as can be done. So there's some flexibility with special use buildings. A swimming pool isn't going to use the same amount of energy as a residential tower. So that is recognized there. And the management of the heating and cooling is often something that will keep people thinking, because if you've got internal heat gains, it's mostly in a building of this size. This is another MURB in Vancouver that's almost finished construction at this point. But they have a lot of internal heat gains. When you've got a high performance envelope, that heat isn't going to get out. So we need to manage that in some way. So in our climate, that heat is typically our main heating source. But you want to make sure it doesn't get to be too much and that it's managed in the summer. So a few basics, and now we're going to come closer to quantity surveying, and everybody can sit up. And we'll look at, I'm not going to put any numbers on the screen, I promise. But I will say a few words that are relevant to the cost of the buildings. And I'm not able actually to put numbers on this stuff. But the principles apply whatever the numbers are, because the numbers vary location to location, of course. But I mentioned earlier that these buildings require a compact form. There's a number of reasons for that. This little chart illustrates it. When we look at the sort of compact form on the left, we move to the middle one. That's an increase of wall area of 10%. And what that means in the context of the climate this little box was modeled in, the exterior, well, the insulation layer needs to be 20 millimeters thicker. That may not be the case here. It'll vary a little bit, but it's the same idea. So what's the cost implication of that? Well, it's not just 10% more insulation. We now have a bigger envelope area. The building is a little bit bigger. We've got, so the whole thing has gone up some more. And you've got a thicker insulation layer, depending on how you're attaching it. What kind of attachments? So you've got now engineered attachments instead of stock ones. What happens? The longer screws are going to be more money. It just keeps adding up and adding up. But you do, and that is still relatively efficient by traditional standards. We see buildings way worse than the middle one. We jump over to something like on the right-hand side. That's a 20% increase in envelope area. The insulation goes up by 40 millimeters. So it's a really dramatic increase in costing. This is an example of a project that we were asked to consult on when I was doing some consulting. I'm not anymore, but I was. And this was part of a larger development, but it was a 23-unit residential building. The group of owners was kind of divided in terms of what they wanted. Part of the group was keen on the design that's on the left. So an architect had designed that to be high performance and affordable, low cost. And we took a look at it, and the question was, can we make this a Passive House? Because a big part of the group wanted a Passive House building. And the architect who did that drawing was loyal to that design. Whatever change we suggested, it wasn't possible to make a change. Nothing really could be changed on that. That was efficient as you could possibly get, and to go to Passive House would just be too much money. If you try to make this structure a Passive House, use this design, that architect is absolutely right. It'll break the bank. But there happened to be another architect that was part of that group that wanted Passive House and is familiar with how you do a high-performance building. And he volunteered, well, just let me take a look at it, and came up with an alternate design, same site, same zoning requirements, same program, same number of units, all this sort of thing, and simplified the design in the way that it shows on the right, and reduced the envelope area by 18%. In that particular case, which I'm not saying is representative of average cases, that project should be cheaper to build as a passive house than as they were planning to build. And we see that type of thing all the time. We'd be given plans, well, here's my house, make it a passive house. And we count the corners. You know, there's 10, 14 corners to get around the perimeter of the building. And for a small build, this is a little bigger building, but on a small building, there's just no way to do that affordably and make it high performance when you've got that much envelope area. So, this is the sort of fundamental architectural piece that drives costing throughout. Some of the, once you've got the architecture down, we can start looking at some of the envelope details, and we won't get into that here. There's a workshop this afternoon where we can get into some of these details a little better, so if you are interested in more details of anything that's discussed here, I'd recommend the workshop this afternoon. But there's generally, you know, the top line talks about insulation or outsolation. We call outsolation the insulation that's on the outside. So typically, it is simpler if we've got, for most buildings, if it's an option, to have the structure on the inside and then wrap it in a nice warm blanket. And the blanket goes all the way around. So you can see on this drawing, we've got insulation that's a good thick layer right around the eave up there in the top corner, goes all the way down and under the floor. This is just a crawl space under here. So these corners are all well insulated. And the window is mounted near the center of the thermal envelope. It makes a huge difference how the window is mounted in terms of the performance and the ability to keep the cold out and the warm in. So it's these sorts of basic design features and keeping it simple. So if you want your air barrier to make it airtight, a good place, depending on, you do the dew point calculation, other things, your envelope consultant will figure all this out depending on the climate where you're building. But in our climate, we typically would pick a surface. If this is a structural wall, it's just a really simple platform frame structure, in this case, a wood frame building. Then we would put the air barrier here where we can make it nice and continuous, and it's out of the way of the trades when they come into here and start drilling holes for electrical and plumbing. And then you've got this robust air barrier that's continuous, it's safe, it's protected, and then you put the insulation over that, and then build your rain screen outside of that. So that's sort of a nutshell of how an envelope may look. It wouldn't matter if it were built out of concrete, steel, or wood timber, big massive timbers. The same sort of principles apply. You want this continuous layer of insulation, a really robust air tightness layer, and check to make sure you've minimized thermal bridging. If you've got a concrete building that goes down to a parkade, and elevators that go down to the parkade, that sort of thing, then you're going to have some good head scratching to do, figuring out how to get elevator shafts and other things airtight and thermal bridge free. But there's products available, thermally broken products where you can minimize the thermal bridge impacts, and in some cases you just suck it up, you've got some thermal bridging, and that's the way it is. But these are all design things that get looked at when the building is only on paper. Here's a drawing and a photograph of the item in place. It's just another example. Again, it's a small, simple wood frame building. But there, it's a little different wall structure than was shown on the other. This is balloon framing. Does that mean anything? Is that a term that's used here? Not hearing it. Okay, balloon framing is a wall. The wall structure goes all the way up, and the floor plates are bolted onto that structure. So the platform framing, you've got one floor coming up here, and one wall coming up like this. You drop the floor on it, and then the next section of wall gets put on top of the floor. So that's what we call platform framing. And balloon framing, you'll have the wall going all the way up, and you bolt a floor onto it. So that's what's happening here, and you've got the deeper sort of structural timber there. what is it, 190? What is it? It's 8 inches, so 190 millimeters. And the lintel here is bolted right here. You can see it's bolted onto the structure of the wall, but behind it is this fabric. This fabric is actually the air barrier. So it is continuous up behind the lintel, and what we'll do is just join this flap here to the layer of air tightness that carries on down. And then the cavity is filled with insulation. So that air barrier is in behind things and out of harm's way. And the floor is just sitting there. And then you don't have the thermal bridging and the air leakage through the building envelope, because the insulation is outside of, most of it is outside of that lintel. So that's what that drawing. Does that make sense? Yeah. And everyone will have their own way to do these things. It's just a matter of figuring out what works best in the local market and the trades you're most familiar with, the materials that are being used, that type of thing. These are just a couple of small examples that we've used. If we've got a lighter building, again, we're not talking a large building with a parkade, that sort of thing, but a lighter building with a concrete, a warm slab, so slab on grade type thing. What we'll have is the concrete is here. I'm not sure how clear this image is at the back of the room. Insulation is outside the wall here, comes down, and it's continuous right under the footing and then back up under the slab. The idea is we keep the slab warm. Your feet don't need to be cold. Canada, we're always worried about cold, but so that's what's happening here. And then the concrete just assumes the ambient temperature, the room temperature, and is no longer cold. And for the wall junction, you keep the insulated wall here. This is the concrete to wood junction. So the insulation is outboard, and this wall is here. There's a bit of thermal bridging here. This is not ideal, and there's little tidier ways to do it. But that's an example of how you try to keep on the inside, make sure the inside surface is always warm. And there's enough insulation there to keep it warm, or in the summer, keep it cool. Now, this is sort of something. Quantity surveyors seem to understand the principle of keep it simple, stupid. And we were doing this project, it's one that I did, and we wanted to put some dormers in to keep the neighbors happy, have it in the design and get our planning approval that way, make it look more traditional. And we priced the truss package. Oh yeah, that's not bad, we can afford to do that. But what we're doing here is installing what's called a service cavity inside the air barrier. So that fabric is the air barrier, and then we just do a very lightweight 2x4, whatever that is, 190 millimeter. Our construction sector is still one that isn't metric, but we draw in metric typically, and then for the trades we translate the drawings to imperial. But it's a lot of fun, and I'm old, so I still use the imperial measurements on timber. But in any event, they're putting this light frame in there as a service cavity, and there's just way too many corners and fussing and fiddling and trying to keep it airtight and so on. It's a big problem. So what happens, this is the building in construction. What happened with that, and how did that translate in terms of some of the numbers? Well, performance. We start with the heating load on the building. If we had built a rectangular building, this building isn't rectangular, it's a bit of an L shape in behind, but had we got rid of the dormers, the heating load would have been 10 kilowatts per meter. Each dormer adds half a kilowatt. It's amazing. So those dormers increased the heating load by 10%, just those little dormers. They were real dormers, they weren't fake ones. We wanted to sell the 12, 13-foot ceilings in the top floors, so we decided we would do that. And then the other thing was the construction cost. All that fiddling around, 2/3 of our labor costs were in the top third of the building. And so that, that was an example of something we chose not to do for later projects. And, the ventilation systems. This is an image of a small individual apartment-sized unit, and it's actually sitting in the ceiling of a bedroom closet. So we had 3-meter ceilings in that building. It's the same building, actually, I just showed. And you just tuck these things into the ceiling. They're meant to be ceiling mounted. They can be serviced like that. Filters changed, that sort of thing. And the magic is that they're quiet enough that they can be in a bedroom closet and not disturb anyone. You don't know they're there. And when you open the closet doors, you don't see them. So they're up and out of the way. And the consumer controls for these units need to be simple. They just need to be sort of 1, 2, 3, and really easy to change the filters. That's a requirement to be Passive House certified. And there's maybe some cost implications. These units cost more money because of the higher quality, higher efficiency. But at the same time, we didn't have to build a separate mechanical closet. We didn't allocate more space. We didn't need to acoustically isolate them from anything. So. Something I'm not going to mention much about here, although I made a quip about it, is retrofits. And that is going to be a critical piece of the puzzle in every country. There is, for high-performance buildings, ways of doing this. And Passive House has what's called the NZIQS standard for retrofits. It is different than the metrics for new buildings because it isn't always possible to achieve the same outcomes when retrofitting an existing building. But the way in which it works most economically in many cases is to do it step by step, because it isn't often that somebody has the opportunity to do a full gut reno on a building all at once. I mean, when that happens, that's great, seize the opportunity. But often with buildings, they're retrofitting them incrementally. The windows go, so they replace the windows. The mechanical system goes, so they replace it. And they don't do those things at the same time because they're not worn out at the same time. So in a step-by-step retrofit, the idea is to identify the order in which the building components will reach the end of their useful life, and then plan for a retrofit that replaces those components at that time with high-performance components that are installed correctly and installed with the next step in mind. So that if the windows are going before the cladding, install the windows in a way that it is easy after the fact to come in, tear off the old cladding, and install new additional insulation and cladding later on. Or if it's a historic building where you can't really muck with the exterior, you're going to be adding interior insulation. If you're replacing the mechanical equipment, install it in a way that you can add insulation later when the insulation gets added. So it doesn't take much to do that and think ahead, but in that way, you can calculate the milestones, the efficiency at each step of the retrofit, and have a plan laid out. So in terms of project delivery, we'll come to a graph in a minute that shows really how important this can be. High-performance buildings require a greater level of integration of the design and construction team. It takes that sort of interaction of people brainstorming together to figure out the solutions. Many of the traditional practices we've had aren't going to work. We'll need alternate solutions that won't seem common. Well, they're not common, and they won't be easy to think of in the early projects. So having that team together in an integrated way can really help make that possible and help with the costing early on. The detail that gets thought through early on is going to be greater than what is traditionally the case. And solving all these problems isn't easy. Right? I mean, all of you have been through budget issues with projects, and when you first look at an issue, it just looks like, well, there is no solution. We're not going to be able to do the project. But you know from experience that if you work at it, you can figure something out, typically. And you can find other ways to do it. But finding the solutions is not easy when you're new in this level of performance. So it really takes committed leadership. That fire hall image that's there, that project will be starting construction very soon. That was a really good example because it hadn't done a fire hall. It's also an emergency command center with a big server farm and that needs all kinds of backup systems. So there's a lot of unusual requirements in that building. And it was an excellent learning exercise for the design team. So a few words on the economics that I've referred to earlier. The first curve is what you would just expect with high-performance buildings. Typically, if I just go back, maybe I'll go back and give it the time. Where we've got the heating demand is 0 at the left-hand side and higher at the right-hand side, and then the cost per meter is the vertical axis. So the conventional way of looking at costing is as performance goes up, costs go up. And clearly that's true at some level. But what the academic study in the 80s showed was there is a point where costs actually drop. And that curve, when you look at all costs, really, there's no data to suggest that a high-performance building costs more than a code minimum building. Because when you take a look at the stock of buildings that actually get built and you plot their energy performance against their cost per meter, you'll find that it's a scatter graph. There is no correlation. And the reason is that these costs that are shown as going up here are actually a small part of the total construction budget. And so the other factors become much more important and simply wash out these escalating costs. But that little drop in costs was found to arise at about this level of performance. And again, at this 10 watts per meter, that is the heat carrying capacity of air that enables these simpler systems. So that's the reason for the little notch being at about that location. And as we move along in the design process, trying to meet these metrics, this is a graph. I don't know if this is taught in every quantity surveyor class or not, but it's got to be a dynamic that you're familiar with. This blue curve here represents the potential to influence project costs over the phases of a project. So if we start at concept right here, we're into design or planning here, construction, and then use. And by the time the building is in use, your ability to influence life cycle costs is very low. Even when you're into construction, it's minor. The time when you can really drive down costs is when you're thinking about the concept of the building and how its architectural form, the general program, its concept. That's where the big savings are. And then after that, it's declining returns. So the question is, at what point in this life cycle do the value engineers show up and go to work? And what capacity is there to really influence costs at that stage? So we need the costing people involved right at the outset. And that's the integrated team approach. A couple of examples of what happens when that integrated team approach is taken, or if the market is just simply let to do this on a competitive basis, because people will figure this out when there's a competitive environment and they're chasing a pot of money. The Pennsylvania Housing Finance Authority decided a couple of years ago that they, in deciding which projects they're going to fund, they fund projects, social housing projects all over the state of Pennsylvania. They decided they were going to give an extra 10 points if it's a passive house building rather than a code minimum building. And 10 points was significant. I think they had a little over 100 points. I forget the total number of points. But it was a pretty good bump. But you could put forward any proposal you like. So it's a very competitive environment there to get their funding. And people tried hard. This is the plot of 179 proposals. That's the size and the price in the American dollars and price per square feet. So the dollar amounts will look like the decimal point is off to you, but it's per feet. So that's what it plotted like. And then of those 179, 59 were proposals to build passive house projects. And the green dots represent the costs of the passive house projects. Now there is, when you do the math, there is a slight difference between the cost of the passive house project and the average cost of conventional buildings, and it turns out to be the passive house projects averaged $171 per foot, and the conventional buildings averaged 168, so they were $3 less per foot. And a difference that's really very difficult to measure reliably. The interesting piece is if you look at the passive house projects that received funding, because there's a bunch of other criteria that the funding authority looks at, the average cost of the passive house projects that got built was where are we here? Was $163.50 per foot. So the average cost of the passive house projects that were selected was less than the average cost of the conventional buildings that were tendered. And what that means is you can do this for less money. You can't count on it. You shouldn't expect high-performance buildings to cost less in terms of capital cost, but there's examples of where that has happened. What we typically say is count on there being some incremental cost, particularly with early projects. But the incremental costs are not that high. So with that in mind, and it's, you know, as we heard with the introduction, some of the ways in which the costs can be kept down is counterintuitive to many people. They'll think of a conventional building, they'll add expensive windows, add expensive ventilation, add more insulation, and they just think the cost is way up there. And that, with the benefit of costing professionals, we can see that that isn't the case. And to me, that's been the magic of watching sort of the Institute here in New Zealand work with other people, seeing the power of having actual cost professionals there who are qualified to express these opinions. It's a huge difference. And that would be very helpful, because in the work we're doing, we all the time get the reaction from those who aren't familiar with these buildings about the cost. And governments just back up because they're afraid of being led to the gallows if they require these buildings, and people get up in arms over costs. So what is it that you as quantity surveyors could do to support the transition to better buildings? Because you really, you know, projects always come down to the money. In the end, things are about the money. And having the money people understand this and able to participate is a huge advantage. So as individuals, what is it you can do? And I would suggest there's several things. Number one, become informed. I've just touched on some of this, but there'll be other presentations. The New Zealand Institute, or Passive House Institute, offers courses. It's possible to become informed. And you may see designs coming forward. You're not architects, but you may, if you are more informed, you'll come to recognize design features that are more expensive. And you can make recommendations or suggest redesign or be familiar with what other projects are costing so you can offer that sort of advice. But just generally become informed on the topic. The other thing is that, at least in Canada, and maybe not here, but quantity surveyors are a rather humble lot. And in my experience, they let others claim their turf. They let others say what costs are going to be. And these others typically have no basis for forming an opinion. They're certainly not qualified to have an opinion. They just have a series of assumptions. So if quantity surveyors stand up and claim the turf of being the costing professionals and speak from that platform, that's incredibly powerful. And if you're informed and then speak in that way as a professional, it can have great impact in market transformation. So that's the other piece. Get yourself informed, claim your turf, and then speak up. You know, Barry, I think it was, yeah, was talking about the world is run by those who show up. And that's really where that thought comes to mind. You show up at public hearings, at in processes that are there to develop policies and that type of thing, and speak as a qualified costing professional, it will have amazing impact. So just speak up, write letters, write reports, do that sort of thing. And I see your institute getting engaged in that. It's really very, very powerful to have that happen. And then, of course, work with others, because by working with other industry groups, whether it be owners, contractors, architects, engineers, you can allay their concerns. Most people will assume that better buildings are going to cost a fortune. But if you understand how it works, you can placate those concerns. You can explain the costing to them. And they will then reduce their anxiety and their resistance to change, and the market transformation can occur much faster. So those are all things that each of you can do as individuals. So why do it? Well, number one, we can maybe help save the planet. That always feels good. Feels good to do that. But number two, it will enhance your profession. The stature, the recognition of your profession. And that's got to be a good thing. Claiming your turf as the costing professionals will enhance the profession in many ways. It can be good for your business to be out there and be recognized as that, for people to see the value that you bring. And good, of course, for your personal reputation and how you function within broader society. So there's all of these reasons to support market transformation. And part of the working with, I would suggest, is with the Institute. And how can you sort of collectively work together to advance this? There's a government in New Zealand that seems my brief exposure to them, they seem very committed to this. They're looking for solutions. They're going to be dependent on advice from people like you to make the appropriate decisions. So there's really a golden opportunity. You know, it's not often that the stars align to this extent, where there's this policy alignment from the global level right down through, you know, national, regional, local city policies, where there's this level of policy alignment. So if we take the opportunity to sort of stand up, to show up, we have the chance now to make fairly rapid progress, especially in a country such as New Zealand that has many of the foundation pieces in place. So I'd just like to close with this message from Amina Mohammed. She's the Deputy Secretary General of the UN, and she speaks about the issue from a global context. She gave the opening remarks to the North American Passive House Network conference in California last year. And that, I think, says something about the priority, the profile this has when the Deputy Secretary General of the UN will address a Passive House conference. We're used to being just this introverted group of building science geeks, and now we've got these people talking to us. So it's really quite a culture shift for us. And, but if you listen to her message, it really applies to anybody. She's talking to this conference that she was addressing, but the same words apply to quantity surveyors and anybody else that's involved in the field of market transformation. So I wonder if we could just cue up that video now and close with that.
Ladies and gentlemen, colleagues and friends, I'm really pleased to send greetings to the annual conference of the North American Passive House Network. Buildings are responsible for 32% of global energy consumption and a quarter of carbon dioxide emissions. Improving this sector's performance is critical for climate action. It will lead to many benefits beyond reducing greenhouse gas emissions, including improving public health, lowering energy demand, and increasing economic savings. This gathering is a sign of your commitment to sustainable energy. Your efforts can make a major contribution to the Sustainable Development Goals and the Paris Agreement on climate change. Innovations in building and energy science have now opened new vistas. Important new possibilities are at our fingertips, where a generation ago, options were few or non-existent. Passive house buildings are at the frontier of technology and know-how. The insights that you're generating need to be applied to the developing world, where millions await the basics of a quality built environment. And your knowledge is also needed in the developed world, which needs to redevelop sustainably. The United Nations is keen to facilitate these advances. For example, the UN Economic Commission for Europe's framework guidelines for energy efficiency standards in buildings are being converted into a global plan for dissemination, education, and action. Successful climate action depends on the collaboration of knowledge leaders, policymakers, and businesses and consumers. We must break the link between carbon emissions and development and replace it with sustainability, well-being, and inclusive prosperity. This is our challenge, and you are valued partners. I wish you all a successful and productive meeting. Thank you.
So this what we're hearing here, it's not something sort of high up and theoretical at the UN level, which can be perhaps a little bit up in the clouds a little bit. But these buildings started, they were the initial research was done in Europe, but there's thousands, tens of thousands of projects there. They've got a long history and experience in developing things there. But it's moved now. China is now developing at a much more rapid rate than Europe ever did. I was told recently that China is going to build more passive house buildings in this year than Germany's done over the last 20 years. They've got individual projects there that exceed 1 million square meters, 33,000 units, that sort of thing. So they're moving rapidly. The market can change faster than people realize. You've seen a number of images from Vancouver here. But think about, and this is one, that's the sort of the scale that they're now getting into. But at the end of 2015, Vancouver had one single-family passive house. Some of you might be thinking, oh yeah, there's actually a co-housing development going in Dunedin. I don't know how many passive house buildings there are in Dunedin. But in many communities here, you'll think there's just one house or two houses, something like that. But that's what Vancouver had at the end of 2015. In the last half of 2017, that is 18 to 24 months later, 20% of their planning applications, we call it rezoning, but 20% of their planning applications for real estate development were for certified passive house buildings up to this kind of scale. And that's an incredibly short period of time. None of those are single family because you don't need planning permission for a single family home. That's about 20% of their real estate development in Vancouver in that period of time. So that's almost unhealthy. Like we need to learn how to do this before we do it. But it is amazing, and it shows how quickly it can happen. So my parting comment is just to say that engage, get ready for a ride, because I think the chances of a ride in New Zealand are really pretty high. And thank you very much for inviting me here today.